Let's take a look at another example. We have a solid gold ball that is floated on an oil bath, so that half the ball is above the oil and the other half is immersed in oil. The oil has a relative permittivity of epsilon r, or a dielectric constant. Your charge Q is going to be released on the ball. We want to calculate a few things. We want to calculate the electric field in space, the charge density on the ball, above and below the oil, above and in the oil, and the charge density in the oil on the boundary with the conductor. So the first thing we want to do is draw a diagram. So this means I have some sort of I have some sort of gold ball. Just do gold ball or gold sphere, and it's immersed in oil halfway through. So halfway through kind of looks like this. And we'll just use like a slab to represent the oil medium. So I have oil here. And a charge Q is released. So first we do a quick explanation of what's happening. Let's analyze the charge distribution. So your charge Q is released on the gold ball. Your top half and the bottom half of the gold ball, are they going to have similar charges, or are they going to be different? So keep in mind that there is a boundary between the two interfaces, and the most important thing is that if I release a charge Q on the gold ball, which is a conductor, there's going to be charge distributed around it, but then that charge Q is going to attract some negative charge from below. So it's going to attract some negative charge from the oil, so the charge distribution is going to be different for the top half and the bottom half. So let's just say, because oil is a dielectric and can be polarized, the top and bottom half of the gold ball will hold or have different charge. But what we can say is that Q is equal to Q1 and Q2. So that is our charge distribution, and we can start solving for the different components now. We want to calculate the electric field. In space. To calculate the electric field in space, what we first have to do is take a look at our spherical structure. We have a conductor, so let's take a look here, and we're just going to draw this again. So we have our gold ball, Because it's a conductor, the assumption is that the electric fields are going to radiate outwards. So we have oil, and up here we can assume it radiates outwards. At the boundary, we can assume it also follows along tangentially. Now looking at the part of the gold ball in oil, we can also assume that its electric field is going to go outwards radially. So we know the electric field should radiate out. At the boundary, we can consider a few things. We know that E1 is tangential to E2. So this is what it's talking about. These two are tangent to each other. And that means I have E1t being equal to E2t. But exactly at the boundaries, the full amount or the full magnitude of E1, so let's do E1 and E2. So the full magnitude of E1 and E2 are basically the tangential components. So we have E1t being equal to E1 and E2t being equal to E2. So this means E1 is equal to E2, and we might as well just give them a common name, E. So we also have the electric flux density. And that's going to be D1 is equal to epsilon naught E1, which is equal to epsilon naught E. So we're moving on to electric flux density. We're going to call this equation 1. We also know that D2 is equal to epsilon naught epsilon R, because it does say that the oil has a permittivity of epsilon R. So for the absolute permittivity, we have epsilon naught epsilon R E2, but we know E2 is just E, so let's call this epsilon naught epsilon R E, and that'll be equation 2. Okay, so at the boundary, we know that the electric fields are identical to each other in magnitude. We know that the electric flux density can be expressed in these two different ways. And what we can do now is apply Gauss' law. So we're going to assume that the sphere has a radius of capital R. Let's just draw this here. And we're taking a look at a Gaussian surface. That has a radius of R, little r. So if we have that, then we can apply Gauss' law and say the integral of d dotted with ds is equal to the enclosed free charge. And how much charge is enclosed? It doesn't matter what the charge distribution is. The enclosed charge is going to be Q, which was released on the gold ball. Now the tricky part here, well, not really tricky, the one thing you have to watch out for is this integral. This is the closed integral of d dotted with ds, so we have to split this up into the top and bottom halves, so into the air, water regions. So this assumedly would be in air at the top. So now we have the integral in air of d1 ds plus the integral in oil d2 ds, and that is equal to q. We can factor out d1, and the total surface area of the gold ball, or basically the hemisphere in the air medium, is half of the surface area of a sphere, which is 2 pi r squared. The bottom half also has the same area, and we have q. We're now going to sub in our equations here for d1 and d2 to try and simplify things. So let's sub in 1 and 2. So d1 was equal to epsilon naught e 2 pi r squared plus epsilon naught epsilon r e 2 pi r squared equals to q. And now we can factor all that out. We have e epsilon naught. We have 2 pi r squared, and then that would be 1 plus epsilon r equals q. And if I were to solve for the electric field, E would be equal to q over 2 pi epsilon naught 1 plus epsilon r squared, and by inspection it's radial, it's pointing radially outwards. So that would be our answer for electric field. Now the next part, we're being asked to find the charge density, on the ball, and that's going to be in air and in oil. So we already found the electric field, so the best thing to do here is to use conducting boundary conditions. So one of the things we want to note is that the electric field on a conductor boundary is associated with charge density on the conductor. So we're going to split our analysis for the gold ball in air and the gold ball in oil. So let's think about it here. E, so previously for the conducting boundary conditions, exactly at the boundary you have an electric field. So that would be E1 when R is equal to R. And that's going to be some sort of charge density divided by epsilon naught, like we've solved for before. We can say rho 1 is equal to epsilon naught. We already solved for E1. It's 2 pi epsilon naught 1 plus epsilon r, capital R squared. And that means rho 1 is equal to q over 2 pi 1 plus epsilon r squared. So we have that charge density. For the gold ball in oil, we do the exact same analysis. We have rho 2 over epsilon, not just epsilon naught. It should be divided by the absolute permittivity. So epsilon naught divided by epsilon r. So we have rho 2 being equal to q epsilon naught epsilon r, very similar to before, 2 pi epsilon naught 1 plus epsilon r, capital R squared. And rho 2 is equal to q epsilon r over 2 pi 1 plus epsilon r, capital R squared. So now we have both our charge densities on the ball in air and also in oil. The last part is asking about the charge density at the boundary. So charge density in oil at the boundary. So we're shifting our analysis to the second medium. So oil is a dielectric. So for dielectrics, we need to find the polarization vector. We know D is equal to epsilon naught E plus P. We already solved for D, we solved for E, so it'll be really easy to solve for P. So P is equal to D minus epsilon naught E. From before, we have epsilon naught epsilon R E for the electric flux density in oil, and then we have minus epsilon naught E. This can be simplified to epsilon naught epsilon R minus 1 E. And we already know what E is, so we can replace that too. And we get epsilon naught epsilon R minus 1. E was Q over 2 pi epsilon naught 1 plus epsilon R squared. And therefore, P is equal to, I guess, Q epsilon R minus 1 divided by 2 pi epsilon R plus 1 R squared. So now that we have the polarization vector, we can then find the surface charge density, because remember, we have a charge released on the conductor and is going to attract some of the stationary or bound charges, bound electrons in the dielectric medium. So if you can remember, we did have an equation for the surface charge density, and that was rho s equals to P dotted with n hat, with the normal vector, when R is equal to R. So let's do this. We have rho s is equal to Q epsilon R minus 1 divided by 2 pi epsilon R plus 1, and then we have capital R squared. But if positive Q is on the gold ball, the assumption is that it must attract negative Q in the oil. So this needs to change, and it's not right. So we have rho s being equal to negative Q epsilon r minus 1 divided by 2 pi epsilon r plus 1 capital R squared. And that is your surface charge density in oil at your boundary.